Hi everyone, welcome to MRM Highlights. It's my pleasure today to present one of the editor's picks for December. The paper's title is Fast Model-Based T2 Mapping Using SAR-Reduced Simultaneous Multislice Excitation. We are here today with Tom Hilbert and Tobias from Lausanne, Switzerland, and David Norris from Nijmegen, the Netherlands. Before moving to our interview, let's have a look at their audio slides.
So now I would like to present our work that we did together in collaboration with the colleagues in Nijmegen. Especially Jenny, Jose, and David, they helped us a lot in implementing our radio frequency pulses, which were really essential for this work. And the main motivation was that basically I was working on quantitative T2 mapping for such a long time. We worked a lot on undersampling, but we realized actually we could maybe achieve further acceleration using simultaneous multi-slice excitation. So as I just mentioned, the main problem is that quantitative T2 mapping is very time consuming, especially if you use a CPMG sequence. And the main motivation is to use model-based reconstruction for undersampling and simultaneous multi-slice acquisition during the acquisition to achieve very high acceleration factors. Once you start using simultaneous multi-slice, you will easily exceed the SAR limitations, and that was the main motivation to use pinch pulses that were developed by our colleagues in Nijmegen. Another thing that we wanted to address in this work is that we have, especially when we use a CPMG sequence, we have stimulated echoes, which lead to a T2 of overestimation. Therefore, we wanted to use a model-based reconstruction that uses a numerical signal model instead of just a mono-exponential decay. So if we look now at our sequence design, it's a CPMG sequence. However, we've replaced the radio frequency pulses in order to have the simultaneous multi-slice capabilities. At first, we start off with a 90-degree pulse, which is a multi-band pulse. So it excites multiple slices, for example, 5 slices at the same time. We could do the same with the 180-degree pulses, so we could use some multi-band pulse here, but we would probably exceed SAR limitations. Therefore, here we used pinch pulses, which have the advantage that they don't deposit so much energy, but instead of selecting a set of slices, you excite an entire comb of slices. But in this sequence setting, this doesn't matter. You can refocus an infinite comb of slices, but you would only refocus the spins that were initially excited with our multiband pulse. And with that, we get our echoes superimposed from all the slices. Additionally, we wanted to accelerate by using undersampling. So we implemented a block sampling, which was developed by Tilman Sumpf. And it basically is a continuous block of case-based samples, where you can see here an example for threefold undersampling, where you have your phase encoding direction from left to right, and your echoes from the first echo to the last echo, from the top to the bottom, and your frequency encoding goes basically into the screen. And you have white samples being not sampled and black samples sampled. And just here another example of a 5-fold acceleration, where you obviously have even fewer samples in case space. In terms of reconstruction, I just want to keep it brief in the interest of time. But we basically took this superimposed echoes and separated the signals from the different slices using a split slice scrub reconstruction, which uses an external reference scan to separate the information of the different slices. After this, we basically have undersampled CPMG K-space, which we can reconstruct with any model-based reconstruction. But we used our own model-based reconstruction that is basically capable of also incorporating a numerical signal. We use the extended phase graph simulation, EPG, to also account for stimulated echoes and get ideally more accurate T2 values than just using a mono exponential decay. Here you can see some results. For example, we acquired a standard CPMG sequence first as a reference, which would take for 50 slices and this resolution, which was 0.7 in plane, about 50 minutes. For comparison, you can see the same acquisition, but using our SMS CPMG sequence. and then going further with even undersampling the sequence. And with acceleration, you see that there's actually no big change in contrast, and the values seem similar. However, we get a noise amplification the more we undersample. And this noise amplification comes obviously from the grappa reconstruction, which amplifies the noise, and also the undersampling from the model-based reconstruction, leading to a certain amount of noise, in this, especially in the center of the brain that you can see, for example, here in this last subject. We did a more comprehensive comparison in the paper, but I will not go into detail in the interest of time. To conclude, we successfully combined simultaneous multislice and model-based reconstruction to achieve a fast quantitative T2 mapping. With that, we could accelerate a standard protocol from 52 minutes acquisition time to 2 minutes acquisition time. And this was only possible because we could use these pins pulses to stay below the SAR limitations.
So maybe to start with, you can like briefly tell about yourself, your background, how did you end up in MRI or maybe NMR?
Okay, so I studied medical computer science in my bachelor's, and this was like I started in 2007, and part of the studies was basically an internship. And this internship I did already here in Lausanne, where Toby was my supervisor, being a PhD student himself.
Right.
And this was almost exactly 10 years ago.
Oh, yes.
And I've never left, and never got rid of me.
Yeah, he kept on coming back, actually. So maybe I continue because you see we are quite intertwined, like our our CVs. I did my studies also in Germany, and I'm also an informatician. I studied something which is called computer engineering at the University of Heidelberg in Mannheim, where I'm from. And then the slippery slope into MR began. So there was a specialty which is called medical informatics. And then I started to learn about MR, and I found it super interesting. And ever since, I'm stuck in MR. I did my master's project on something like diffusion simulator, with which I came here for my PhD then in 2007. Yes.
When I started.
Yeah, and David, now your story.
My history, a short history. Yeah. Well, I've been in MRI my whole professional life, so and that is now getting to be rather long. So I'll try and keep it short. So I studied physics, and afterwards I did a Master of Science in medical physics, actually in Aberdeen in Scotland. And it was a medical physics department, and every year they had one PhD position, and it rotated between the different groups in the department. And when I finished my master's, I got kind of told if I wanted to do a PhD, then this was my chance in this rather strange new thing of what was then called nuclear magnetic resonance imaging. So that was back in the early 80s. And actually, I kind of realized again in recent years that I was very privileged, because I did my PhD actually on the world's first whole body MR scanner, which was working at 0.04 Tesla, which is a proton resonance frequency of 1.7 megahertz. So I did a PhD in flow imaging, and after I did that, I went to Bremen in Germany. So there's a German link for all of us. Actually, I stayed in Bremen for quite a few years, and 8 years, I think. After that, I moved to Leipzig, and that was in the period after the Berlin Wall had come down. So I was kind of one of these pioneer foreigners, and I worked for the Max Planck Society in Leipzig, which was a very interesting and formative experience for me. And I came to Nijmegen in 2001, and I've been working here happily ever after, but I still haven't lost my German connection because we have a collaboration with the University of Essen across the border, and we had then Europe's second 7 Tesla system at the Erwin Hahn Institute, and I'm still, well, I'll be going there tomorrow, and I'm still active there.
Okay, cool. Then let's move to your exciting and interesting paper. Tom, would you like to tell us a bit more the story, the idea evolved, how the behind the project, and so on?
Sure. So at the beginning of my PhD, I was mostly working on like accelerating the quantitative T2 mapping and basically mostly on the CPMG-based sequences. And what we started off with was undersampling, which was the first obvious thing to do to make the sequence faster.
Yeah.
And back in the day, we worked with the group in Göttingen from Jens Fram and especially Tilman Sumpf to actually accelerate the sequence with model-based reconstruction. And the thing is, we hit very quickly limits there in terms of acceleration. So I think we managed like an acceleration factor of 5, later a factor of 10. And at some point, you didn't have enough samples, or your SNR went down so much that you couldn't go faster. And then we were thinking, okay, would that undersampling be compatible with simultaneous multislice? But the problem there was you have these 180-degree pulses that have like so much power deposition that if you would like do a multi-band pulse with them, you would just exceed the SAR limits almost immediately. But then there was this connection of David and the other Siemens guys that were like, hey, why don't you use these pins pulses that the guys in Nijmegen developed basically. And I think this is how it got initiated. And this was, I think, in like 2013, 14, when you went there the first time.
I'm afraid so, yeah.
So, and this is when we got the pulses and started working on it. And like first simulations showed that actually the undersampling is compatible with doing simultaneous multislice. And then the heavy work of like actually implementing it in reality, so having simultaneous multislice and the undersampling at the same time, this was like the bulk work basically of the entire project.
Yeah, exactly. So so for maybe here, if you also describe what is special about the pins pulses, that would be also great. I know it has probably a longer history, but just for the audience also, I think it would make a better link here if we tell what is special about it.
So obviously David is the expert for the pulses, but from my point of view, in a simple way, is that in order to do simultaneous multislice, the first thing or the easy thing you could do is to just multiplex multiple pulses that have different frequencies. But the problem is the multiplexing, it often results in these peak amplitudes that might be even clipped by the scanner, or even this like hitting the SAR limits. But with pins pulses, you are actually able to avoid this by, instead of multiplexing pulses, the way I explain it, I'm not sure if David is too happy about it. I see it like you take your pulse and you undersample it, resulting in a like an aliasing of your pulse, resulting in a comb of slices that get excited instead of just a few slices. And obviously you do this aliasing very controlled, and I think David has a much better explanation from a mathematical point of view. And I don't know if you want to chip in there.
No, it's really a good, you know, it's a good explanation. You have to see the peak voltage, which you can try to get around that problem by kind of changing the phases of the pulses you're adding in together, but you cannot get around the fact that the power in the normal sort of multiplexing procedure is proportional to the number of slices that you're trying to excite. So, and if you think of a turbo spin echo sequence, this thing runs away very, very fast in terms of power deposition, which is the advantage essentially of using. I mean, you can look at it in different ways, but the way Tom explained it is basically just the Fourier property of multiplying by a comb function in the time domain will give you a convolution in the frequency domain, allowing you essentially to excite an infinite number of slices for the same power, basically, as for a single slice in the ideal limit.
Right. Okay.
That's using the power of an artifact, if you will. And one special little trick, and I remember when we were sitting in Nijmegen really a long time ago, is and that is something the colleagues came up with, of course, because in the initial PINS paper there's only sagittal acquisitions, because you can, if you have an infinite comp of slices excited, then you don't want all that signal, right? So if you go transversal, you don't want the body signal. And one thing you can do in this very acquisition, which is very practical, is, and what Tom did then, is like the excitation pulse. You do a classical multiband pulse, which is like heavy on SAR, and I think we have 16 echoes, like, so I have 16 refocusing pulses. They are these low SAR PINS pulses, which are infinite in a way, and that but since you have only excited transversally the slices you want, with the multiband, the PINS pulses only act on these excited slices then.
Okay, wow, that sounds clever.
But here comes the practical problem, making this work on the scanner so that these different types of pulses really refocus the same slices that you excited and match them in terms of like bandwidth, and also you want a refocusing pulse a bit wider than the excitation pulse. It became tricky quickly.
Yes.
Okay.
So that was a bit the challenging part for that pulse part.
The dirty truth is that I actually tried, like I started this project and I tried it and I didn't manage. Then I also changed roles and he made it happen then. With a lot of help from David and Jenny and Jose, actually.
Wow, that's cool. That's the power of the group work, I believe.
Indeed.
That's great, yeah. Okay, thanks a lot. So I feel like that there's also a second part of the project which is powerful or different, is the signal modeling part. Would you like to tell us about the modeling part of the project?
Sure. So when I started working on this, you would be typically using the mono exponential decay, and then removing the first echo to like avoid some stimulated echoes at times. But then it mitigates the stimulated echoes if you just remove the first echo, but then in reality you still have an overestimation. And one of the problems we wanted to solve here is also to get more accurate in terms of T2, and this meant to like extend the model in order to also simulate the stimulated echoes and incorporate them into the signal model. The thing is that the stimulated echoes, they come from like inaccurate refocusing. So you have to take into account your B1, but also your slice profile of your pulses. So we ended up with a very complex model, which was not analytical anymore, but in the end it was an EPG simulation that gave for us the most accurate model.
And EPG stands for? Just for?
That's the extended phase graph simulation. And with that simulation, we got very nice results that seemed to fit the data well. And then it was a huge workaround basically to get this numerical model into the iterative reconstruction. And this is what we call the SAFT reconstruction. So it's a split algorithm for fast T2 mapping, where we basically separate the reconstruction into a data consistency, so trying to enforce similarity to your raw data, and a model consistency term, where you try to enforce your reconstructed image to be similar to your simulated signals basically. And that, yeah, that took a while, but this was part of my PhD, which this type of reconstruction I could reuse in several projects, and we're still reusing in other projects. So it was also like one of the major outcomes, I think, to develop towards this direction, which goes also with the trend to actually use dictionaries instead of an analytical model.
Right. Yeah. Exactly. It's good to use those keywords nowadays also.
Yeah.
Okay, so now I'm checking like your figure 5 in your paper where you had the estimated T2 maps, relative difference maps. Can you discuss a bit maybe the reason behind those popping up ventricle CSF regions?
So yeah, I mean, obviously these pop out very obviously, and the thing is like we're using 16 echoes. I think it was roughly 10 milliseconds echo spacing.
Mm-hmm.
We end up at 160, 170 milliseconds as the latest echo. But then the T2 of the CSF is way higher.
Mm-hmm.
And the effect that we see there is not a lot. So I would say the T2 value of our CSF is way out of our measurement range.
Okay.
And even a little change in noise or signal amplitude will make a huge impact on the estimation there. And by just changing the pulses does have an impact, obviously, and just independent if it's just a similar SMS pulse or just a single excitation pulse, I think it will make a difference there. And I guess this is why it really pops out there.
Yeah, exactly.
Just to add, because I mean, this protocol is optimized for the T2 values you see in the brain, in brain tissue. And if we were to measure CSF, that's basically the message here, you would have to adapt the protocol accordingly to actually measure this very long CSF T2 values.
Okay, I see. Oh, thank you. So yeah, this is, I think, also nice to discuss in the paper, like a discussion in the limitation kind of part. So I also enjoyed reading it because the rest is like the gray-white matter part is looks really cool. And I mean, it's the speed up is like 50 minutes to 2 minutes or something like that, which is really great.
Yeah, it's because you combine the power of undersampling and simultaneous multislice.
Yeah.
Because they're really like orthogonal to each other, so you can really exploit them to their maximum, basically.
Yeah.
So that gives, like, if you have an acceleration factor of 5 in the slice direction and an acceleration factor 5 in plane, then you end up with 20 to 25, which is like really a lot. And I think this is very similar to like the philosophy that you have, like if you have a 3D acquisition, then you can use all the nice compress sensing acceleration, which works much better on these huge volumes. And this is basically similar to what we're exploiting here. All of a sudden, you use the entire volume to accelerate, not just a single slice. And I think that helps a lot to reach acquisition times like this, actually.
Right, right. Great. Do you have anything you would like to add, David?
No, I mean, I really enjoyed the collaboration. I thought the paper was fantastic. I mean, you know, to get to these acceleration factors, it's really a tour de force, right? So, and you know, the data look excellent. So I hope that in the long term there's some kind of implementation on at least on the Siemens systems.
Right.
And with the move to more quantitative MRI measurements, I think this sort of thing can be very important, and it can really bring something for patients. Because I mean, a normal T2 measurement was completely out of reach in the past, whereas now it's possible.
Yeah, exactly. That nicely brings me to my last potential question. So do you want to comment on any clinical value, any obstacles, and like potential future directions to overcome that?
So, I mean, clinical value, David basically said it already.
Yeah.
If you do a standard T2 map, it's just so long in terms of acquisition time. If you want it in a reasonable resolution, you won't be able to put it into a clinical protocol. I mean, I don't think any radiologist would put a 20-minute, 30-minute protocol on top of the standard clinical routine to get a T2 map. So the clinical value would be here that we actually achieve acquisition times that you can put into a clinical protocol or a research protocol, and then start to investigate what biomarkers you can use, like T2 values in a certain region to detect a progression in some certain disease or something like this. I mean, that's the real value, that we basically enable clinical research to find biomarkers and ideally use that at some point in a clinical setting. And in terms of like future work, I think we should really try also to use this on other organs. For example, the cartilage is really interesting in terms of T2. So having a fast knee acquisition would be great. Also, we saw in like prostate cancer that you can actually predict the aggressiveness that you typically find out with a biopsy by the T2 value of the tumor. Okay. So that would be extremely interesting to like allow like a full coverage prostate protocol to acquire fast T2 maps in a clinical routine.
Okay, I'm not. Yeah, sorry.
Just because well, I think we are very excited here in general about quantitative imaging, and I think on a more general note, I think we have now from the acquisition side this technique and others which actually allow us to create those maps reliably, robustly, but also in a time which is clinically feasible. But now I think the whole field is a bit on the stage. Okay, what now? And there's different things you can do. Of course, I mean, these things also help if you want to do some classification, because it's better comparable for humans, but also for machines, obviously. So you filter out some of the effects you have in like traditional relative contrast imaging if you feed this to any whatever machine learning thing. However, some things we are excited about here is also to create normative databases. So basically, you do this kind of acquisitions, or you acquire this kind of data on a lot of healthy people, and then you know if a person of like 45 years old male, what kind of T2 values they should have in this organ, right. And then you can start to compare, and this actually makes it only then clinically viable, because with the T2 value itself, a clinician can actually nothing do with, right? So I mean, it's as such, compared to a like relative contrast, what they're used to. But if you say, okay, this is actually different from normal, and it's actually so much different because I can even quantify the difference.
Right.
I think we all think here that this brings the value actually.
Yeah. So it's kind of where you're looking for like a robust reference data set, so to say.
Exactly.
Like
and this all starts with a robust and fast acquisition.
Yeah.
And I think we have a couple of those now in the field, and now people have to build up on that, I think.
Okay. I just wondered something. I'm not so familiar with body imaging sequence-wise. Would there be any problem with the fat water or something like that in the sequence, or?
So in terms of there's obviously a chemical shift. So if you have a low bandwidth readout bandwidth, then you have a fat shift. Mm-hmm. But we did try it in the pancreas, mm-hmm. and we do get reasonable results. And I think the fat doesn't make too much of a problem. The problem rather is motion. So because you undersample and you put a model in there that doesn't know the motion,
yeah,
it amplifies the artifact the moment you introduce motion in there. So we put all sorts of triggering in there, and then it made it better. But I think it's like once you reach the higher abdomen, or even you're close to the lung, then it becomes more difficult.
Yeah. Although
reusable T2 values,
pulsation and physiology comes.
Exactly. That's more of a problem than actually the fat signal.
Yeah. True. Okay. Great. I think from my side, those were my questions. Do you have anything you would like to add that I might have missed?
For the paper?
Yeah.
No, but I think just one thing is, and David said it already, I think there should be more of these collaborative things, because I think it's not very common that two groups, even though we are like a half a company group and so on, but like, actually work together on a project. I think this was really, and it was a lot of fun. We had these regular video meetings just like now, and we were having a lot of fun. It was really like speaking to friends every 4 weeks or something. I think that was the frequency. And yeah, no, that is also another like more social part of this paper.
Yeah.
And it was also perfect because like the guys in Nijmegen had this, were experts in the pulses.
Right.
Coming more with the undersampling and reconstruction. And it was just a perfect combination. And I think like that's why we could reach so high acceleration factors. Otherwise, we would have just stick to one method instead of combining them.
Yeah, yeah, definitely. I also joined actually in 2016, I think it was, SMS workshop in Donders, at Donders.
Oh, right, yeah.
Yeah,
Okay.
yeah. Yeah, exactly. So that was also really, really nice. Yeah. Okay. Great. It was really great chatting with you guys.
Yes, it was
Very nice talking to you as well.